we're finally putting all these variables you've learned about together and starting to look at the atmosphere's really circulations, which are really the key to forecasting what the weather's going to be. We want to understand the circulation so we can know how the weather is going to impact our area. So we're going to start this one just by looking at like a global planetary overall circulation. So if you averaged out the atmosphere circulations, this is kind of the picture we want to look at. We got a lot more detail we're going to get into about our local weather and stuff in the next part of this week's discussion. But let's look at this a little bit. So what are some of the principal features in this planetary scale circulations, and how do they affect our weather and climate? Well, all right, we know our Earth rotates, and we know that we don't have an ideal simplistic way of looking at the weather because of all of that. If you had sun on one side of the earth and dark on the other, you would have a lot of convection on one side and none on the other. So everything would sink down there. You just have two big circulations. We don't have that. So what happens is, because the earth rotates and we're constantly getting the sun angled differently, we have different belts of circulations. And there are three main ones. The equatorial ones are down between 0 and 30 degrees north. Think about it. Almost no fronts make it into that area. They're kind of all tropical. Then we have our area, 30 to 6 degrees north, the westerlies, where we live, where we have a lot of cold front passages, warm front passages. It's kind of a boundary region for all the tropical weather below us and the extreme cold in the North Pole, where 0 to 30 degrees, where 60 to 90 degrees north. So think about them as in the ones close to the equator, very warm, very moist. Close to the North Pole, very cold, probably very dry. And we're the transition zone. So with that, we have high pressure, literally, that typically forms right around 30 degrees north and low pressure around 60 degrees north. So if you were to look at an idealized picture, now remember, these things are going to change from January to the summer because they're going to move north and south. In January, we have a very intense series of lows you can see going across Canada, and you get them all winter long. What happens, though, you still have a lot of high pressure out over the Atlantic. Summertime, bigger high pressure, a little further north, too, in the Atlantic, and weaker lows, but still around 60, maybe even a little bit north of 60 degrees north. Notice that most of the southern hemisphere is just water. So you actually wind up with more simplistic circulations down there because of that. So we have talk about the subtropical oceans here and the anticyclone around 30 degrees north. South of that, you have winds coming out of the east, basically. So if you were in a sailboat wanting to go from across, like Columbus did, and he got south of 30 degrees north, that's why he came in much further south, because he just followed the trade winds that are down there. Poleward, you have more subpolar lows right around the Arctic, and you have a lot more fronts. And you might also have a very strong polar highs, some of them very cold and very deep, very powerful. So we also have in the wintertime a polar vortex. Northern hemisphere, it gets strongest in the winter. Southern hemisphere, it's strongest down there in their winter, our summer. And with that, in between, we have the mid-latitudes where we live, and we have a westerly flow, but you'll notice it kind of wavy. It's not nice, smooth, west to east. It kind of goes up and down in nice little wave patterns. So the tropopause then, with that in mind, you have a much higher tropopause down between 0 and 30 degrees north. Remember, you don't have cold fronts and coming down there really. So you have really good heating, and all that heat makes the air less dense. It pushes the tropopause higher. To the north, from 0 to 60 degrees north, it's extremely cold. All year long, it's fairly cold. So the density of the air is greater, tropopause is lower. Now, the mid-latitudes, there's all kinds of things going on here with the convergence of air masses from the south into the north. That causes the tropopause to vary a lot. So it makes it kind of a little bit more interesting, shall we say. South of the big 30-degree north high-pressure systems are trade winds. These trade winds tend to be fairly stable aloft. So if you were actually over islands like Hawaii, trade winds wind up not having a lot of thunderstorms. They get a lot of rain from the low, from coming in to the mountains, but they don't get much in the way of thunderstorms because the air is fairly stable aloft in these trade winds. Now, the intertropical convergence zone varies. And you're going to get a question this week. It's going to want to know why it changes more over land than over water. Well, guess what? Look at the oceans. They hardly move. And why is that? Well, because the oceans don't heat up that much. It takes a specific heat of water is very, very high compared to that of land. So the oceans don't really have a great variation in temperature over them. It moves it a little bit north or a little bit south depending on the season. But now over land, on the other hand, India, China, they got lots of land there that really heats up in the summertime. So what's it do? It allows the ITCZ to move north so that it changes literally the flow pattern in these areas. And what does it do? Well, it creates monsoons. They're literally winds that blow from the same direction over an extended period of time. Well, if you move the intertropical convergence zone north, what happens is you get a very southerly flow into that intertropical convergence zone. Lots of moisture, lots of rain. They have a very, very dramatic rainy season. When the intertropical convergence zone starts moving north early in the summer, passes different parts of India, the monsoon sets in. The same holds for Indonesia, Southeast Asia. Wintertime, however, you look about it, all that cold air up in Siberia, the intertropical convergence zones move south. Guess what? The winds are all coming out of the north. So they get a very dry monsoon. And you can actually see on the edges of these intertropical convergence zones a difference in climate. San Diego is on the eastern side of the Pacific High. What does it get on the eastern side? Well, the eastern side is going to have north winds. So instead of coming out of the tropics, they're coming out of cooler area. They're also going to tend to bring in cooler ocean temperatures. San Diego's ocean temperatures are significantly cooler than they are over in Charleston, South Carolina. So they wind up being a lot drier. Now, Charleston, South Carolina, on the other hand, the winds are coming from the east and around the bottom of the high and up along the east coast of the United States. The Bermuda High, the air is fairly unstable. It's humid. Get lots of showers and thunderstorms in the summertime. And here you can see the ocean circulations that are set up. Look at the Gulf Stream here coming out. It's part of the North Atlantic Gyre moving north, and it really heads towards England. It actually helps keep Iceland and England a little bit warmer than they normally would be because of that circulation around the North Atlantic Gyre. All the ocean circulations are set up because these are the average wind flow in the atmosphere. The atmospheric winds generate these ocean circulations. We also have a monsoon in North America. It really impacted the western part of the United States for quite a while there this summer. What happens is you get heating. There's actually a mountain range over western Mexico. The top of those mountains heat, producing high pressure, literally aloft. Remember, you get the low pressure at the surface, but because of the density of the air, you wind up with high pressure aloft. That low pressure at the surface pulls in moisture off the Gulf of Mexico and from the southern Pacific Ocean, you wind up having a lot of rain over that area, but you wind up having high pressure above it that allows it to stay in place for a very long time. So that you wind up, but that's the rainy season for places like Tucson, Arizona, and parts of New Mexico. Rossby waves are long waves. We just looked at the waves in the atmosphere. I want to show you this actually right now. And it's hard to really picture a Rossby wave. This is a 500 millibar chart looking at the northern hemisphere. What you see is low pressure here, down through here. You see another low pressure over Europe. Kind of have a little bit of a low kind of inching down there as well. Those are Rossby waves, big areas of low pressure. Now, if I were to look in detail across the U.S., well, I might see a little wave here. There's another little wave here. Oh, there's another little wave here. And in Europe, there's 1, 2, maybe even 3 different they're short waves. What happens is these short waves rotate around the globe, but when they come into areas where a Rossby wave is, they actually tend to deepen, and they reach their maximum intensity there, and then they tend to weaken after that. So one of the things meteorologists look at is where the general Rossby waves are, and they vary. They will move and change with time. So by knowing that, you can actually pick out areas where these little short waves might actually intensify. So now that we've looked at the Rossby wave a little bit here, so move on here a minute. And here you can see patterns of zonal flow across the U.S. or the world, and especially in the mid-latitudes. When the flow, and in the summertime, zonal flow tends to be very fast from west to east. Not a lot of a ridge here, so you're bringing up a little bit of warm air here. You're bringing down a little bit of cool air here, like here as well. But once in a while, you get these meridional flow patterns, and they can happen any time of the year, particularly in the wintertime more, but they do happen in the summertime. Systems are going to be slower moving from west to east. Look, they got to go all the way down here, back up, whereas they just move to relatively short distance here. And look at all the moisture and warmth that's going to come up on the east side of the meridional flow, all the cold air coming down on the west side. It's going to generate a much greater temperature contrast and a lot better potential for significant extratropical cyclones to form the low pressures. Then there are blocking patterns. Let's go back again here, because there actually is one that is occurring right now. Look at this low sitting out over the Atlantic Ocean. This low can't get through there because there's a ridge of high pressure here. So it is blocked by this low pressure right there. These happen periodically. So that is a blocking pattern. Basically, you get a circulation in the atmosphere that just sits there, blocked off from the rest of the flow. It's just rotating right here. Normally, this would be all big bridge. But because there's this one low pressure here, you have blocked the rest of the flow from going this direction. And it changes how the atmosphere then would move along. So, continuing on, here are long waves and blocking systems, and when they set in, you get some tremendous historic rainfall patterns like happened in 1993. Much more rain than normal sometimes. Jet streams are another part of global circulation. We've heard aircraft talking about jet streams, and I am sure if you tune on the TV meteorologist in the wintertime, oh, well, the jet stream is doing this. They might be talking about it. Think about it. There's a slope in the atmosphere. Closer to the tropopause, there's a greater slope. So the jet streams form very high up in the atmosphere, and they go pressure gradient from high pressure to low pressure, it's going to form a very strong wind speed in there because the pressure gradient is going to be stronger the closer to tropic pause you get. And the Coriolis effect balances this. You wind up getting geostrophic winds many times in the jet streaks. And they'll develop typically where the polar front is well defined, so you have greater temperature contrast. And they can reach speeds of over 200 miles per hour. They'll shift. In the wintertime, they're further north. In the summertime, they're further south. If I wanted to show you a jet stream right now, let's just take a quick peek at this. Our jet stream's way up here right now. There's a little bit kind of buckling in the flow here, but most of our jet stream, and especially over New England right now, is where the jet stream is very strong. One of the other aspects of the jet stream is where there are jet streaks within the jet stream where there's stronger winds. These jet streaks kind of correlate with, I was looking at short waves in the atmosphere, shorter wavelengths. And they have divergence in the left front. Here's the strongest max. The left front would be right here. And divergence in the right rear. What does that mean? Well, we know that divergence causes the atmosphere winds to move apart. It means the air from below rises. It causes low pressure at the surface. And guess what? Low pressure typically brings us the bad weather. So moving on from this, now that you've seen what they actually look like here, let's move. And here's your ripple, and here is your divergence along it. And here's the actual low pressures. Think about it on the back side. Typically on a wave, you have convergence aloft. You're pushing down. You're going to form high pressures behind the low pressures. And here is your typical jet streak. Now, there are a couple other global circulations, El Nino and La Nina. El Nino is a warm phase to the southern Pacific sea surface temperatures. La Nina, on the other hand, features a cold phase. And La Nina typically has exceptionally strong trade winds with it. And El Nino, the trade winds tend to weaken. And El Nino also tends to bring more systems across from the Pacific into California. A lot more rain typically for California. There's a warm phase for El Nino, and La Nina is the cold phase. And they're an ocean and atmosphere circulation combined. You can't get rid of one without looking at the other. And here's just a whole bunch of them, how they oscillate back and forth. And and here's the Ekman spiral, which is just the water being rotated around. And it continually gets pulled to the right by the Coriolis effect. So it gradually, literally, if you were to go to the Outer Banks, many, many times in the summer, you have a continuous southerly flow there. What happens? The water begins to move from the south to the north of the Outer Banks, and it begins to rotate to the right with an Ekman spiral. And eventually, it's going to rotate all the way back around the deeper you get. And when it does that, that water down on the bottom ocean floor is going to come up the slope and replace the water that was on top. And there have been times I've watched the temperatures in the Outer Banks go from 80 degrees to the next day in the 50s, all because of things called the Ekman spiral. So here we're just talking about the El Nino and La Nina impacts, and you can see here the warm phase, a lot more thunderstorms, a lot more moisture over the Pacific coming east. Cold phase, typically less thunderstorms are further west, and wind up with less rain coming into the United States on the west coast. So again, I want to take a look at something here with this. We'll just take a quick peek at La Nina right now. And hopefully it will come up. Here we go. All right, we are heading into La Nina right now. So we're heading into a cold phase. These are anomalous temperatures. compared to the 1991 to 2020 database. And you can see here, parts of this part of the ocean are well below normal here. So it's actually a cold phase beginning. An interesting thing is we also have buoys that actually reach down and look at temperatures down low in the ocean. So with that, when you do that, what you see changing is we had a cold phase last winter. We went into a slightly normal phase. We had a lot more ocean heat. Notice how the ocean heat has just plummeted in the last several months here, last month. So this is what's leading the forecast that there'll tend to be a La Nina event coming up this winter. So with that again, back along here, we'll go to a North Atlantic oscillation. It's another global feature. It has a major impact on the eastern part of the United States. It's a variation in sea level pressure from the subtropical high to the subpolar low. And it governs the strength of the North Atlantic storm track, like where we get a lot of nor'easters or lows coming up on the East Coast, and when there's very cold air coming out of Canada and the eastern United States. These have a major impact on whether that's going to happen. They're very difficult to predict, but when we get it right, we can actually do a pretty good job, and they will persist literally for a month at a time. And there are implications for both the negative phase and the positive phase here, and impact. And you can see here they vary, but they typically last 2 to 3 weeks at a time. The Arctic oscillation is another one. In the wintertime, you have a very strong polar vortex that sets up. The stronger that polar vortex is, the more positive the Arctic oscillation is. And the cold air is trapped up in the extreme north. It doesn't allow you to get that extreme Arctic air down south into the United States. When it begins to shift towards a negative and gets weaker, that circulation, the cold air can get into the United States, and that is when we get our extremely cold outbreaks. So this is something that is forecast into the future, and we look at this to try to determine maybe next week or the week after we can expect a major Arctic outbreak coming into the United States. It's really, again, hard to say what the whole winter is going to look like. But if you were to monitor this and see the changes setting up with it, you can get an idea whether the polar vortex is going to weaken and allow strong cold air into the United States. And it has a positive and a negative phase. And then there's specific decadal oscillation, which is just another one of these. Same things, has an implication, especially for the Pacific and the western United States. Madden-Julian oscillation. There are strong thunderstorms that form over the Indian Ocean. When they do, it kind of almost like jerks the atmosphere, you'll say. And when it does that, it triggers waves in the atmosphere that literally circle the globe in 30 to 60 days. And depending on where they are around the globe, they have an impact on weather. You can actually watch this circulation transfer around the globe and restart over again. And when it does that, depending on, it may impact and actually help generate tropical cyclones. It may intensify extratropical lows over the United States. And it may help and enhance precipitation from atmospheric rivers coming into the western U.S., depending on which phase it's in. So it has a major impact on global weather. And I think that's about what I wanted to cover with this one. So hope you got something out of this. Let me know if you have any questions.